Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm Tom Ball, and it is my great pleasure to welcome Brandon Lucia back. He was a researcher at Microsoft Research, and now he's an assistant professor at Carnegie Mellon University. He does amazingly cool stuff with hardware and runtimes, and he's about to launch into outer space via SpaceX, some cool little circuits, and I guess we're going to hear a little bit about what the challenge might be if you want to put something in outer space that doesn't have its own battery pack.
Yeah. Cool.
Hey, welcome back, man.
Yeah. Thanks for the introduction. This talk won't be about space entirely. It's going to be about a general problem that we run into in space, which is intermittently available energy and energy harvesting. So there's a lot of different design challenges that you run into when you're trying to build devices that you want to run off of energy that you're borrowing from your environment. So I'll talk about what the challenges are, then I'm going to talk about some system support that we built for that that kind of dropped last year, and then I'll talk about some stuff that we have going on right now, which is kind of the state of the art in debugging devices that are doing intermittent execution and energy harvesting. I'm from Carnegie Mellon University, the Electrical and Computer Engineering Department, and the stuff I'm talking about is what I've been doing and my students have been doing together. So it's kind of big, happy family group effort from over there. So. Probably don't need to tell you guys too much. The motivation for this kind of work is that we have little devices everywhere. So your medicine bottle isn't just a medicine bottle anymore. There's like a computer in there that's telling you how many times you've opened the lid and where did that come from and where is it going. So you know if your medicine has been somewhere that you don't want it to be or in the hands of someone that you don't want it in their hands. And these devices are in the medical domain. We can put these devices into space and they can do things like try and find resources extraterrestrially that we want to mine and bring back to Earth and lots of other really cool stuff. So emerging devices are everywhere. And a lot of these, especially if we're looking at kind of medical applications, we need the devices to have high reliability. In particular, things that are expensive or dangerous need to be reliable. And so for the most part, when we build devices using little embedded systems like this, we are tied to a power source, like two AA batteries, or maybe you have to plug into a USB, or maybe you have some big chunky power pack or something like that. So this is problematic because these devices, you can't put them everywhere. They're not tiny. It's hard to put them, say, inside of your body for medical applications. And if you're going to launch something into space, you probably want something more sophisticated than 4 AA's that you're going to go and shoot it into space. Or if you want to monitor a volcano, your AA's are just going to catch on fire and go away. So that won't work. So we're looking at the result of kind of years of research on something called energy harvesting. And energy harvesting is a technology that effectively untethers the device. So here's how it works. This is the basics. You have an antenna, which is an energy receiver. You have a capacitor, which is an energy buffer. It's just like a bucket you're pouring electrons into. And then you have kind of the downstream application hardware. So this is a computer, it could be a microcontroller, you can have sensors, you can have a radio so that you can send communications from your device. But the basic model of operation is you have some energy source over here, like this big square antenna that I have on the slide. You have some empty space. This can be 20 meters, 40 meters, that kind of range. It's not infinite range, especially if you're using this kind of like an RFID reader antenna as your energy source. And then you have a target device like this kind of janky breadboard mock-up prototype that we built in my lab that is implementing some application. So the future, what we hope for is that someday you can cram one of these things in your head and it can help you to understand, say you have schizophrenia or say you have autism or something. This can help you understand why you're behaving a certain way on a certain day. These kinds of applications, I mean, these are the exciting applications, doing things in especially medicine that we can't do today because you don't want to be cutting someone's head open to replace batteries or to power it. And that's literally how these things work today is you'll have a power pack and you need to charge it. So this is a big shift. This would be a kind of dramatic shift from the way things are done today. So there's
By the way, for illustrative purposes, or is this a?
That is for illustrative purposes. This is effectively kind of clip art. This is some existing medical procedure. I think that thing in the center is. I think this is actually a battery. I'm pretty sure that's a coin cell.
Oh, okay.
So I think this is a probe that someone put in for a short-term experiment. Now this is a probe. That's some computation, probably a radio. And I don't know about this particular image because I just, this is from Google, but
okay.
yeah.
So we don't know the provenance of this image. I was just curious.
Yeah, we don't. But in general, experiments like this, I mean, they're short-lived because you have to take them out and replace the battery. That's the big problem here. Yeah. So if we go to this energy harvesting that I was just describing about, where we can take energy from the environment, we can use radio waves, we can use solar energy, and we can power these devices. There's a caveat, and that is that the energy that we get is intermittently available. We don't always have energy available. If you're near a radio tower, then you have lots of energy. You can soak it up and fill your capacitor and run your device. But if you go far away from your radio tower, then suddenly you don't have anything available. Your device turns off. Even if you're near a radio tower, you charge up a capacitor, and then you start running your device. That drains the capacitor, and when the capacitor is going to drain much more quickly than it can charge up. So when you run your device, unless you're very careful in software, and that's actually an open problem, how to be careful in software, you drain the capacitor. And so you essentially, the device just kills itself at the cadence of the charge and discharge of the capacitor. I'm going to tell you more about that, but that should give you an idea that these devices are inherently unreliable. This is an important point. They're inherently unreliable because you don't have a continuous execution model, because the energy is intermittent. So
that latter problem, can I solve it by having a switch between two capacitors and charging up one while I'm using the other? That doesn't seem, if I do have the energy.
You could do that, but it's not going to entirely solve the problem, because then you have two things that are going to be charging unreliably, and you have to power the logic that switches between them. So, okay, what if we had three? Let's add three capacitors. Now, we can switch between the three. We may not have charge in any of them that's adequate to run our device, and now we have to have more sophisticated reasoning about which one we're going to use. So we can try and fine-tune the power system. I think we should attack the problem in software. And so that's what I'm going to talk about today, is actually how we can take this on in software. And there's a little bit of hardware stuff I'll talk about later, but primarily I'm going to talk about how we can solve the problems of the intermittent execution model, which I was just describing, and how we can think differently about building systems, and in particular building software for these kinds of systems. I'm going to talk about some system support that we've built for making intermittent executions reliable. And then I'm later going to talk about some very recent work that we've been doing on a hardware-software platform for debugging intermittent devices. So this is filling the gap, the absence of a tool chain for understanding intermittently executing devices. Okay, so to give you a clear idea of exactly what it looks like when we're running on intermittent energy, we have a plot here. The y-axis is the available energy, and we have time going across the bottom. And here we have a lightning bolt indicating we have some radio frequency energy being transmitted over to our device. And so we charge, and then we hit the lifeline. This is an important point in the timeline of this device. When you hit that point, it turns on, you start operating, the device can use its sensors, communicate, whatever. And when we're operating, you see we precipitously drop off in the amount of energy that we have. The capacitor is being drained very quickly because maybe we're being naive about how we're using the energy in the software. Then we hit the death line. We run out of energy. By the way, the lifeline, it's around 2.4 volts for a lot of microcontrollers. 3 volts is the kind of standard operating level for microcontroller. 2.4 volts, just to give you a concrete idea of what the parameters are here, is kind of what that lifeline is. And 1.8 volts is the death line. And so if we're looking at kind of 100 microwatt operation, that should give you a ballpark of the kinds of devices we can support. With this model, with radio frequency charging in particular. So we hit this death line, cross over, and then we're not charging, we're dead, we're far away from the radio antenna, and we can't get any energy. A little while later, maybe we get some more energy, we're charging, and then we hit the lifeline again, and okay, cool, we can start operating again. This is a complicated plot because there's a bunch of continuously varying parameters. We have energy level, and we have to find a way of measuring that accurately, and time is moving forward. So part of the work that we've done in defining intermittent execution is abstracting some of the details away. The way we abstract it is by noting that here the computer shuts down, and here the computer reboots. So really, instead of charging and discharging, all we need to see from the software's perspective is that we have a sequence of periods of reboot and computation. The red parts are when the device is turned off. The green part is when the device is operating. And this is what we call the intermittent execution model, and this is stuff that we published at PLDI in 2015. The intermittent execution model says you compute for a while, then you drop out, and then some arbitrary period of time later, you don't know how long it's been, you don't know what environmental changes have happened. That's the intermittent part. You turn back on, and you start computing again. And our goal is to make computations that go longer than one green box. That's the hard part. So just to look at what it looks like to run a computation, if we have some code that looks like this, you want to append some things to a list. We have a main function at the top that's going to append 10 things, and then we have the append function, which bumps a pointer in your list and then puts a character in the location that's pointed to in the array. So let's run this on intermittent energy and just see what happens. We could maybe run for a couple of loop iterations, then we get a reboot. Okay, well, we're going to start over then. And we're going to do one iteration, start appending, and we're going to get a reboot. We can do this all day, and we'll maybe make it as far as 3 loop iterations or 4, depending on the size of our capacitor and the amount of energy we have. But we're not going to be really successful at doing any useful computation if that's our model. So we noted that we can model intermittence as a control flow problem. So this is a control flow graph, and it maps to the program that I just showed you. And we can add edges to the control flow graph that essentially go back in time. So you're at some arbitrary point in the program, and according to an external environmental condition, it's not a data-driven control flow edge, but instead it's a kind of environmental one, you go back in time. And so these are implicit control flows. That's one thing that's really hard about this. There's nothing in the code that says from here you could go back to the beginning of main. The programmer has to reason from each point in the program that they may be able to go back in time. This is hard. Even if you're very clever, and you decide to use some kind of checkpointing system, which I'll talk about in a minute, this problem doesn't go away. So a big challenge to doing intermittent execution successfully is dealing with the fact that you can go back in time. These devices that I mentioned, intermittently executing energy harvesting devices, typically have a hybrid memory system. So what do I mean by hybrid? The hybrid is between volatile and non-volatile memory. So a small amount of volatile memory is typical, around 2K, and then a larger amount of byte-addressable non-volatile memory is typical. And a lot of microcontrollers these days are using something called FRAM, which has reasonably low access latency and energy, although it's still much higher than SRAM or DRAM. So we can use the non-volatile memory a lot like we use the normal RAM in the computer. And of course, we can use the volatile memory just like we would normally, except that the volatile memory has this peculiar property, which is that its values disappear. So if we want to span periods of failure, then we have to deal with the fact that our memory gets erased all the time. And the non-volatile memory doesn't disappear. It keeps its values. This is straightforward, but I'll show you in a minute that that gets problematic if we start using the non-volatile memory just like RAM and we are also using some volatile memory like RAM. So zooming out for a minute, the big idea is that the tools we have and the mental models we have for building software don't align with the intermittent execution model. And in fact, something that is correct when you have continuous power gets really weird and sometimes incorrect in unintuitive ways when you do intermittent execution, especially when you start mixing together non-volatile and volatile memory. And so I'm going to talk about a new category of bugs which are related to intermittence and the hybrid memory system. I thought this was a really gross comic, which is why I included it. Okay, so I'm going to talk about intermittence bugs now. And you guys can stop me if you have any questions along the way. I'd be happy to keep taking questions along. The first intermittence bug that I'm going to talk about is an out of thin air value that you can get. And this shows up, okay, so the setup here is we have the same program we were looking at before. Now, we could say that there's a checkpoint at the beginning of that loop, and we can go back to that checkpoint. And now the setup for the checkpoint is we're capturing the volatile state of the program. And when we fail, we're going to reboot, repopulate the volatile state. We're not going to do anything to the rest of the non-volatile state because it seems like we don't need to checkpoint that. It's non-volatile. We can just keep that around. And so we'll go back to this checkpoint at the beginning of that loop, and we'll execute forward again. So if we do that, we can see that size and buff, they're in gray. That means they're in the non-volatile memory. And they're initialized to buff is an empty buffer of characters, and size is -1, meaning we have nothing in the list right now. So if we run the program like I showed you before, we get through incrementing size and then putting a character in the buffer. This is pretty straightforward. This is easy to understand how the state gets manipulated there. And then we fail. So we were at this point. Let's say we hadn't made it around this loop. Like I said, there was a checkpoint there. So each time we go around the loop, we're going to checkpoint and say, OK, we captured that we did 1, 2, 3 loop iterations. But we died right at the end. So now we're going to restart. We're on loop iteration 1 again. But that non-volatile state doesn't get erased when we turn the power off. That's going to stick around. And so what we see is we have an out of thin air value. A gets appended twice for the I equals 1 iteration. It's a buffer state that should never exist. It's impossible. In a continuous execution, we won't be able to see this behavior. In fact, we can run this out to its kind of natural conclusion. Let's keep going around this implicit loop. It's still loop iteration number 1. But if we just turn the power off repeatedly like that, we're going to keep updating that buffer. And eventually, we get the size to 11. That's a value we could never see before. We have this array. It has 11 A's in it. That's a value we could never see before. So we can produce values in the execution of a program that if you run on continuous power, you would never encounter. And the important thing about this is the failure is dependent on the availability of energy and the rate of charge and discharge of the capacitor. That should be concerning, because that means if I'm using radio frequency energy to charge my device and the transmitter is here and the device is here, I can do this and change what the software does. That's a system behavior you probably don't want. There's another kind of bug that we encounter. This is an atomicity violation in the conventional sense of an atomicity violation. Some things that should happen all at the same time don't necessarily happen all at the same time, and you get values that end up being weird. In this example program, we want the increment of size and the population of the buffer to be atomic with one another. And we can clearly see that if we kind of execute up to the point where we're incrementing size, and then we have a failure, and then we restart, well, we've incremented size twice, and we only put one character into the buffer. So now we have this weird atomicity violation manifesting as corruption of the state. You have the size equals 1, and you have the first entry of the buffer is unpopulated. So atomicity violations are another problem we run into. We can get memory corruption in the non-volatile memory. And remember, we're using checkpointing here. We're preserving all the volatile state in a checkpoint, and we're going back and repopulating it. OK, another problem that we can run into is if we have some high energy cost piece of code, we could get into a situation where we start at a checkpoint and try to run forward, and regardless of how hard we try, we just can't make it through the region of code between the two checkpoints. And this is something that could vary in environmental conditions, rate of charge of the capacitor, and the programmer has no visibility into whether their program is likely to, or with what likelihood will succeed. And so this is problematic. We eventually end up in an infinite loop, and this program works correctly if you plug your device in. That's one of the big problems here is the programmer is probably going to do most of their initial development using continuous power, and they'll say, my program works. All I have to do is foo, and then high cost, and then whatever. And in fact, when you go over to the intermittent power supply, you're going to see that this program doesn't actually appear to do anything. So I've given you some evidence that these devices are too unreliable to put inside your body right next to your heart. I wouldn't want to do that. And we need better programming abstractions to make these things reliable. And I think we need system support to go with the programming abstractions to enforce some reasonable guarantees on the behavior of software that's running on intermittently executing devices. So we came up with a couple, and I'm going to not go into a lot of details because I've given some rendition of this talk at Microsoft before. So I'll skimp on some of the details here, but I'm going to give you an overview of the kind of system support that we have in mind to make these devices more reliable. So in PLDI 2015, we had a system called DINO. DINO is an acronym for Death is Not an Option. And this addresses the problem that I pointed out before, that checkpointing doesn't get us out of this mire. If you have non-volatile memory in the system and you have volatile memory in the system, you can end up with these problematic, inconsistent memory states where your non-volatile memory has values in it that you don't expect. So if we take a program like this one, we can convert it into a collection of tasks. Tasks are demarcated by static boundaries in the program, and tasks are dynamically defined. As you flow through the statements in a program, you may traverse across a task boundary that ends the previous task and it begins the next task. Our system supports task atomic semantics, meaning that when we start a task, if it completes, then it's as though that task executed without being interrupted by any power failures. So we eliminate the atomicity violation problem, and we eliminate the out of thin air value problem as well. The way that it works is by selectively preserving not just the volatile memory, but also grabbing pieces of the non-volatile memory that through program analysis we realize that we need to preserve, otherwise we'll end up producing those funky memory states that I showed you before. Another important thing is that we eliminate these effective control flow edges, these implicit backward control flow edges, because we have these task boundaries that have checkpoint semantics with regard to control flow. So when we have a failure, we go back in time to not an arbitrary point in the past where maybe a checkpoint was collected or to main or something like that, but rather to a point in the program that the programmer statically defined. this is helpful because now we can understand from, if we look at the program, from a certain point in a function, there's a small set of points backwards to which we could go on a failure. So we've eliminated this kind of arbitrary implicit control flow problem that we had before. Yep.
It seems like all of the bugs are related to, they're very similar to concurrency bugs, concurrency-related bugs. And this has a feel of transactions in some sense with atomicity for a single task.
Yeah.
But transactions are really hard. So are there other things that people have solved in concurrency that can be applied in this domain?
Yeah, this is a great question. So this is a lot like concurrency. And in fact, in the paper that I have cited here, and you could go and take a look at it, we frame this problem as not just the control flow model I showed you before with implicit backwards control flow edges, but also as preemption. And it turns out that if you have two preemptible tasks that access the same state, which is like a data race, then you can have one of the problems that I showed you before. Now, with regard to the similarity to transactions, I think you're right on the money with that. We want transactional semantics. We want tasks to be like transactions. There's a few differences that make this model maybe a little weird, but also really implementable. One of those is that we have kind of statically bounded but dynamically defined regions. So you can have, this is kind of a weird thing. Transactions are typically scoped with a beginning and an end, and each beginning has one end. In our case, you could have an initial boundary and then some statements going forward, and then a branch, and you could have a terminal boundary on either side of the branch. So now there's, for that given start task boundary, you have two potential end task boundaries. So that's just a kind of mechanical difference from transactions. We do have some problems that transactions also have, like open nesting and I/O, and the fact that you have a world that you're operating in, and the effects of that world, whether it's through other software modules or through I/O interfaces. It could make your life more difficult for preserving the atomicity of your tasks. Yeah, great question though. I think we want a lot of the same guarantees transactional memory provides. And so going forward, we've actually been looking at how we can kind of take some of the big ideas there and boil them down. So we're constrained in a way that a lot of transactional systems aren't, and that is doing rollback is expensive. We need to consume memory to store a log of everything that we've done, and if we encounter a conflict with some previous failed incarnation of the same task that we're trying to execute, we need to go and repopulate from that log, or maybe replay parts of the execution. We have a flavor of that here. Going forward, though, we need to move away from that model. So that part of transactions, I think, is similar now, but should not be similar in the future. It's too expensive in this domain. You can't spend the energy to go and repopulate the entire state of memory based on, after a failure, based on some log or something.
It also seems like, correct me if I'm wrong, that another difference is that there is no such thing as a local access. There's every single memory access you do is in a transaction, whereas in a TM system, you just get to take advantage of the fact that some of the things you know are only going to be written locally, right? Mm-hmm. There's no such thing as local when everything might be subject to power failure.
Yeah, that's an interesting point. So something I'm not going to talk about today, but we could talk about some other time, is distinguishing between volatile memory and non-volatile memory, and treating volatile memory more like local memory and treating non-volatile memory more like global memory. Because you have this nice property that when you fail, your volatile values all go away. So you don't have to worry about partial results being preserved across a failure like you do with non-volatile memory. So in a way, that's sort of like your local memory. Nothing else can mess with it. No previous executions can mess with it. But you need to make sure that you reinitialize it every time you start a task and then run forward. So if you apply that programming discipline to your volatile memory, it begins to look a little more like the local memory in transactional memory systems. Cool. Other questions? Yeah. Cool. So I'm not going to dig into this in excruciating detail because the example is pretty simple, but this figure shows how our system that I just described with tasks and checkpointing and selective versioning of the non-volatile memory eliminates bugs. So here's how it eliminates the out of thin air value problem. We capture the checkpoint, and this captures those non-volatile memory locations. And it should be straightforward to see that if we preserve those here and then fail before we hit another task boundary, when we restart, as long as we restore the values of buff and size that we had before, we can go forward and we have a consistent state of memory. This should be pretty straightforward. So we're essentially adding to the checkpoint is one way of thinking about it. It's important to point out that prior work on this overlooked the need to do this versioning of non-volatile memory. So there are systems out there, software systems and hardware systems actually. There's another paper, and I'm not just picking on mementos here. There's work called Quick Recall, a system called Quick Recall that implemented volatile-only checkpointing in hardware even. And if you add non-volatile memory to the mix, which I think their devices even probably assume, it's problematic. You get the wrong result. So I can pick on this one because my co-author on the paper that I'm talking about here is a co-author on that paper too. So he happily welcomed the correction. So the question though is, which parts of the non-volatile memory do we have to capture in the checkpoint? Which parts do we need to version? And we need to make conservative assumptions because we want to do this statically. We want to decide in advance. We can't do any runtime reasoning. That's too expensive. So if we have a task boundary, we have to say which parts of this program do we have to capture? Well, we can look at how data flows. So if we look at our control flow graph, we can see how data flows along the control flow arcs in that graph. And we can see that on the implicit edges that we added, if there's no flow through non-volatile data, then we don't need to capture that non-volatile data as part of the checkpoint. So you can see here we're just assigning into this non-volatile array. We're putting I into the bin I in that non-volatile array. And so we don't need to preserve it because when we restart, we're going to go back to the task boundary and we're going to just blow all those things away. It seems this is straightforward that we don't have to capture those. However, if we change this program a little bit and we say that we're going to be incrementing each of the bins in this non-volatile array, now the story is different. Now we do need to checkpoint that because we have a data flow around the loop that's created by that implicit control flow edge. So if you store something and then you restart, you're going to see the result of what you did before. You're going to see the incremented value, and you'll get wacky values all over the place. So the key insight here is that we have to version the data if we both read and write the value. That's something that we can look for in the compiler, and that's actually what we implemented. We looked for situations where we have both kinds of operations, and that's a superset of what we need to look for. That was conservative. We can trim it down, and we could have trimmed it down. That's what we did in our compiler because it was easy to implement, and it works to keep things correct. Yeah?
More precise would be upwards exposed uses, downwards exposed definitions, right? You need to really see a data flow around them. You need to have a use which is upwards exposed, which means there's a path to the use from the beginning of the task. Right?
But some of those are okay because if you have an upward use,
you have to have a definition that
right, and a definition later. Yeah, but I think that produces a data flow around the implicit control flow arc.
Right.
Yeah.
Right. So so you can make it more precise than read write.
Yeah, so we're being conservative. We're saying if we see both of these on the path to a task boundary, then we would preserve that in the non-volatile memory. So, you have a question?
I was also going to take a shot at summarizing the exact requirement. I was wondering if it is exactly idempotence.
We want idempotence.
Yeah, so it's like, I'm just saying anything that is idempotent is free. Anything that is not idempotent.
Oh, yeah, that's true. That's true. If you put a task boundary at a point that defines all forward tasks to be idempotent tasks, in other words, it encloses, it never cuts one of those edges,
right.
Then every checkpoint is free. Then every one of these boundaries you put in is free.
And then every amount of checkpointing you do drags you toward idempotence, and once that's in, and once you're done the checkpointing, then you have idempotence.
Maybe. There's another factor, and that is sometimes you don't want to put a checkpoint, or sometimes you want to put more checkpoints, both of which could mess with idempotence. The reason you might want to do that is if you have I/O and you want to, for example, put task boundaries tightly around I/O, or if you need several I/O operations to be part of the same task because you're correlating values from two sensors, and if you collect one sensor value now and one 10 minutes from now, then it doesn't make any sense. So subject to those other constraints, which, by the way, are not edge cases, they're very real in this environment. Like, this environment is all about I/O. You're doing sensing and you're processing and you're transmitting. You may be able to get those idempotent things, but not always. Yeah, but it's a good observation, yeah. Okay, so this example does reveal, we're caught up. Reveals a fundamental limitation of checkpointing. and this really sucks, and this is something that we're trying to get away from because it's very expensive to implement. This is what I was saying to you just a second ago. If we can't know in advance where we might be accessing, we need to capture the whole thing. And that's a huge drag, especially when your task boundaries could be subject to external constraints like the position of I/O in your code. You could be really hosed. I mean, this is a really contrived example. We have a million entry array and we're choosing a random element of it. That's probably not what we're going to be doing. But you can imagine how this manifests as control flow deciding which things you're going to be accessing. So my view is that in the future, checkpointing is not a viable solution for solving the intermittence problem. We need to do something else that preserves state, keeps it consistent, gives good guarantees, but isn't reloading values every time we restart. So we built a prototype. This is sort of an unremarkable prototype. It's the way that you would expect it to be if you've done this kind of work before, and I know most of you have. So we start with a program. You have to put these annotations in. Our compiler does a data flow analysis and finds those situations we were just talking about and links us to a runtime. And then when we get over there, we have a runtime library that the compiler links it to, and it does checkpointing, and it does the data versioning stuff dynamically as we need to. As you cross task boundaries, that's the implementation. We evaluated on a bunch of different benchmarks that we got from kind of various places. We have a MIDI musical instrument interface. We have sensor logs, some various stuff. We implemented for a custom breadboard prototype and for the WISP-5 platform, which are two different radio frequency energy harvesting devices. And if we don't use any support for these things, we have errors and the systems don't work. All of these applications produce the wrong result, or they have a hard stop failure that we can't recover from because, for example, the histogram that we were storing sensor log readings into is corrupted. One of the bins got unlinked. And so now what are we going to do? We have no way of recovering the value. So if we look at one benchmark, like an activity recognition benchmark that takes accelerometer readings and decides using a nearest neighbor classifier whether you're having a tremor, which is kind of a medical condition that we could identify pretty easily. This is a wearable medical device kind of application. Then we can see how much error do we really get if we're running at, say, 10 centimeters or 20 centimeters, pretty close to the power source. This is a radio frequency power source. And these distances are fairly short because we wanted high fidelity in the experiments without having to do 26 gazillion measurements. As you go further away, the variance becomes higher in the measurements, so we would have had to do more. So we went out to 60 centimeters, which is not kind of notably far. But we saw that even out there, we had edging toward 10% error in our measurements, and that's pretty close. So if we want to use this device in a real environment where, say, we have instrumented rooms in a hospital with RFID readers, and we're going to be going in and out of range, say 10 to 20 meters of these things, we're really going to have to improve the fidelity of this because the error seems to scale, maybe with a diminishing trend toward higher error at higher distance.
So suppose that I have that exact scenario where I'm in a hospital, and one question is, are the errors uncorrelated? Because you could imagine having two devices, for instance. If the errors are uncorrelated, if it's really particularly like a kind of a blip in the air, right? Then the probability that actually both devices, for instance, have an error when I enter a room goes down exponentially. Right?
That's a good idea. I think we should probably do that. Using the issue is going to be.
But it depends on the correlation of the error. It depends on I'm kind of asking about the error.
Correlate. So I don't know if the errors are correlated. I suspect. Part of me wants to say yes, because you'll have more errors if you have more failures. And so if you're further away from a power supply, you're going to be dropping out more frequently. So that means that both systems are more likely to be failing, and so they're more likely to have errors. But then on the other hand, it's a function of the software. And so we don't know. They might not be in the same place. They might be just out of phase enough. Maybe this one, it could also be a function of the hardware. Maybe you use different memory technology in one device than the other to try and be more robust. An issue that I see in implementing this kind of system is that you have a distributed system now, and if they're computing the same value, they need to agree on which value they computed. Or you need to build your application in a restricted way so that they can produce an arbitrary stream of values, and you know that whatever the streams are that the two devices compute, you can put them together and make something sensible that your application cares about. In either case, I think there's some distributed systems coordination stuff. You're not going to run Paxos on these things just because there's not enough energy to take checkpoints, so good luck with Paxos. But I think you would have to do some coordination stuff. They can communicate. They could actually communicate with one another, and that might be one way out of this. Cool. So with our system, ta-da, no error. That's because we eliminated by construction. So the point here is that we can compile programs differently and get better reliability guarantees for these inherently unreliable devices. That's the punchline. We eliminate the error because we compile the program differently and put runtime support in to prevent these things from happening. Okay, so now I'm going to switch. Sorry?
Just something that shows the cost.
So the cost, I don't have it in the slides, but in the application we were just looking at, it's hard to measure the overhead, but it's about 2x slowdown on the baseline implementation, with the caveat that the baseline implementation is incorrect.
Right.
So it takes about twice as long to complete the computation, and that's not just because we add more cycles to each loop, but because if you arrive at a task boundary and you're at, your bucket's half full, you have to do more work, and so you're more likely to fail, and then you have to go back to the beginning of the task and spend a quarter of your bucket to repopulate the memory, and then you can complete the task that you were doing. Mm-hmm. So it's not just the additional work of per task overhead, it's the additional work of wasted work in failing in tasks that you wouldn't have otherwise failed in. So that's why it's 2x. That's why to me, this is a surprisingly high overhead number for kind of sparse checkpointing, because we're manually placing checkpoints. The checkpoints can be as sparse as we want them to be. So that's why it's 2x, though, is because we have not just more work per task, but because we have more failed tasks. Yeah.
So this is, I'm not sure if my question's fully formed yet, but I'll try it. So you kind of made this comment that checkpointing is where you guys want to move away from it, because you had this very concrete example of accessing an array that's a billion elements. Mm-hmm. And it seems like that's your programming model is very low level, like you're C, right? And so one thing you could think about is a set of abstractions where you're still allowed to have checkpointing, but you've put the right kind of data structures, whatever those things are, that let people do certain class of operations easily, where you can still be amenable to checkpointing. So part of the question, I guess, to kind of come back to the question is, have you thought more about programming language abstractions that help people do this type of work, as opposed to checkpointing? And maybe that's like stealing the rest of the thunder. So I don't know.
No, it's not the rest of this talk. It's actually a talk that 3 months from now, I'll be giving that talk or something.
Okay.
But yeah, the basic idea is that we can do it sort of like decomposing checkpoints into the individual memory locations that we want to be accessing. And if we force the programmer to adhere to a discipline in the way that they use their non-volatile memory, then we can eliminate the need for checkpointing, but still have idempotent task restart. And so we can talk more about this offline. It's basically roughly what you said, except that we're not using any kind of ADT abstraction. It's more of a kind of general, you can think of it like as a kind of key value store abstraction. And then working forward from that, you can do arbitrary computation, build up arbitrary data structures. Yeah. The task abstraction is pretty similar, though. That's roughly the same. It's a little bit different, but it's roughly the same. Yeah. Cool. So if we want to debug these things, we have all these weird bugs. We need to change the game a little bit, and I'll show you why we need to change the game a little bit. Debugging is a particularly hard problem because the intermittent behavior that we're seeing not only causes conventional software errors like we're already fairly familiar with, but it also can lead to kind of the hardware misbehaving in ways that are apparently invisible. And so both of these are problematic. I'm focusing on software here, but I wanted to mention that there's the possibility for the hardware to go wonky too. So debugging is something we need to be paying a lot of attention to going forward. Okay, so I showed you before how we can get intermittence bugs, and these can lead to application errors. Like if we have 11, then this is obviously a problem. We don't want 11 entries in our 10-entry buffer. And we note that this failure only manifests when we're running on intermittently available energy, when we're running on intermittent power. So if we have the radio frequency harvester pointed at that device, we're going to get this bug manifesting when we have a reboot here, halfway through our loop, and then we start again and we execute and we increment. Okay, now we're at 11, now we have this problem. So we don't want this to happen because this doesn't correspond to any continuously powered execution. Our group is approaching this set of problems with that as a correctness definition. So when I say we're debugging, we're trying to move toward a more correct program, we want to permit behaviors that are permitted in continuously powered executions. This is a reasonable definition of correctness that we're pushing towards. So what do we need to do to understand why this bug happens and how we can fix it? What we need is to look at how the energy is changing, like on this curve that I showed you before, and what's going on in the program at each of those points when the energy is changing. So here we have size incremented and buff incremented, and then we had a failure. on that curve. And we saw, when I showed you the example and explained it, we saw why that was happening. But if you're just writing an application and 1 out of every 10,000 executions fails, good luck figuring out that this is what's happening. You have events A, B, and C on the downward slope of your discharge curve. Then you restart and you have A and B again, and that leaves you with a corrupt state. This is difficult to reason about because we don't have any visibility into the device. We want to be able to answer the question, what was happening when that weird thing happened and we saw our application produce the wrong value? What was going on inside the device? So the problem with trying to diagnose this type of failure is that typically we're in this kind of cartoon setup. You attach a big chunky plastic box to a power supply, like a USB port, and you attach the other end to your target device. You have visibility into your device. This is great. You can do JTAG debugging. You can get all the logic bugs out of your program, but you're providing power. So your discharge curve looks like this. You're at full voltage the whole time. This grayed out part never happens. You never see the bathtub of kind of discharging and then recharging again. So we'll never get 10. You can run it as many times as you want to. You're only ever going to see 10. So that's a real drag. We can see the failure behavior, run on intermittent energy, but not be able to look inside the device and use JTAG or use any kind of debugging console. Or we can power the device and we can look at all the registers and everything as the thing's executing. That doesn't help us very much because we'll never see the failure. This is the problem that we have. This problem is called the energy interference problem. And no devices that are on the market today or from research solves this, addresses this.
Couldn't you just, again, taking the idea that this is an instance of a concurrency-related bug, use concurrency-related tools in an emulator? So for instance, I could imagine, is there...
You just said use an emulator. So the emulator is the problem there. You'd have to be able to model the behavior that is causing your bug in the emulator. We don't necessarily, I mean...
You could just effectively, okay, fine. But it's a non-trivial mapping, I get it. But you could imagine, maybe you could say something like, your memory, you have maybe I could take this offline because I'm not sure how to answer my question. But the point is that it seems like you could come up with an interleaving, for instance, of an execution, of a concurrent execution that gives you a value of 11 for your SC bug. If you actually change things to be global memory.
Yeah, that's interesting. We actually had a short-lived project that we haven't followed up on, which is essentially simulating arbitrarily timed power failures and hoping that a single power failure leads to the corruption that we're looking for. We found that while sometimes it is, in other cases we needed multiple power failures to get something really bad to happen. Otherwise we wouldn't end up getting the wrong value.
But the power failure is just a backage, right, in your control flow.
It's a package. It's one of these implicitly defined packages. Yeah. So we could go in and instrument the program and
to add that package.
Yeah, I mean, let's get together and build that thing. Man, I'd love to. Yeah, we need the hands. That's what we need. So. Yeah, that's a good idea. And the connection to concurrency is deep. Like I said, in the PLDI paper, we kind of identified this, and you can use the same kind of theoretical framework for reasoning about this. Data races in particular are a nice way of thinking about it. Yeah. So then here, we can also use logging. Logging is great. If we have an intermittently executing system like this, then we want to understand what the behavior was. We could, maybe log the energy periodically, or we could like blink an LED or something. I mean, the peripherals that we have are pretty limited. Printf we could implement over like a UART, and that's great, but all of these things cost energy. And so we're effectively changing the discharge curve by putting this stuff in. It's an observer effect, and in some cases it's pretty rough. If you want to blink an LED when you have some condition, like maybe you blink your LED when you're adding an element to the list, and you want to see, and then maybe you're blinking another LED when you get down to 1.8 volts, so you know when you're about to die. If you can see really fast when those LEDs are blinking at the same time, that might be when your failure condition happens. So think about that as your kind of optimistic, hopefully this works kind of debugging model. This is actually what people do. People do things like this when they're doing embedded development. And it gives you a situation like this, though, where you're killing the device by doing a log and trying to blink the LED. So even if that would work, you're changing the system's behavior, and you get this energy interference gap where the behavior that you're looking at is different by some constant amount of energy from the behavior that you are trying to investigate. So you may mask that. There's also the problem that you need to know more or less what you're looking for in order to log it and try and find it. It's the same as doing any kind of tracing printf-based debugging. So this is pretty bleak. This isn't the way forward. This is a stopgap at best if you can make it work, if you can find some signals to get off your board. You can use an oscilloscope. That's a nice idea. I just sent a proposal for one of these, and it came out to about $29,000, including all of the probes. If you want digital probes to grab a few signals coming out, you want to look at energy. By the way, the correlation between what your program is doing and what the energy is doing is totally invisible to the oscilloscope because you can't probe the internal logic of your microcontroller. So if you want to get a good measurement of what the energy is, you can do that with the oscilloscope. This isn't the way forward either. Maybe combining the oscilloscope and logging and doing logging while you have an oscilloscope trace, that's how we developed what I'm about to tell you about. And I can tell you from that experience that that's extremely difficult and time consuming, and it wastes a lot of time with false starts because the instruments begin to lie to you after a while. So it's hard to debug these things. Oscilloscopes, logging, direct measurement, none of these work. So we developed a new thing, which is called EDB. This is the Energy Interference Free Debugger. And this does the things that I described us wanting before. We can correlate program events and failures and certain value conditions being satisfied and certain energy conditions being satisfied with the energy behavior of the system. The device that we designed, I have one right here. It's real hardware. We built this in my lab. We laid out the board. An undergrad actually did a really awesome job laying out the board. I was impressed. It can not just monitor the program state and the energy state. It can also manipulate the program state and the energy state. And we support all the kind of conventional, familiar debugging operations like assertions and breakpoints on values or energy. We have an interactive shell. We have like a Python library with an interactive shell. So it's really easy to use. We've kind of tried to make it as simple as possible so that you can really debug these energy harvesting devices in the same way that you debug normal embedded systems. So as for monitoring, we have access to all of the program state. We implemented a little thin client runtime layer that we can ask questions of, and then it sends us values back. And we can read the target energy level, which is nice because then we can correlate those points in the program that I just described, identifying using that client runtime layer with direct measurements of the capacitor on the device. We can read I/O messages. We can actually decode things as they go by through the I/O layer by capturing on this board and then proxying the communications out. So we intercept and then forward is one way of doing it, or we can passively just monitor the communications as they go by. So we can grab I/O, we can grab program state, we can grab energy, and this is all passive. And it's all energy interference free. I'll tell you some numbers at the end, but I think here we were like nanoamps of current. And so if you think about 2-ish volts, this is a negligible amount of power. This is an amount of power that doesn't make any difference over the long term.
I don't quite understand from the slide why it's so cheap. What does that in the other board make it cheaper than logging? Why is it so cheap?
Why is what so cheap?
Why is reading the target energy level and like reading program state, why is that so cheap?
Because all we're doing is using the ADC on this board. And we don't need to use the ADC on the target board if we connect wires at the right place. And so that's why there's this 6-pin header on the bottom here. If we pop this onto the header that we designed to fit onto, in our case, we targeted the WISP-5 because it's kind of the most mature platform that's out there right now. Then the pins that we connect to their power read, they expose the power over a couple of lines. Then we can read that.
Continuously powered.
Oh yeah. So this USB port would normally be plugged in. I should have mentioned that. Yeah, we're continuously powered, so we don't get any interruptions. So we have a continuous, UART connection to a Python console. We can give commands all the time. And then this thing is blinking on and off like it normally would be, 1,000 times a second or something, and we can reliably get state out. Now, say we want to do some more expensive monitoring actions than just reading the energy level or reading target I/O or hitting a breakpoint or something. To do that, we need to be a little bit more sophisticated. We need to be able to manipulate the energy level. And what we do is we lie to the target about what was happening. We can charge up to compensate for energy that the target uses doing debugging operations. So if there's a whole bunch of kind of ad hoc breakpoint-like debugging operations, we assess how much energy that took, and we can top up the capacitor. If we want to go into an interactive debugging mode, we can just power the device, record what the energy level was, power the device, and then go into arbitrary debugging activity, and then reset the energy level to what it was before we went into debug mode. And we've implemented all that, and we can get, again, it's a variation of kind of, I think, 2 to 4% of our capacitor is all we kind of, the error that we insert in the energy level of the device. So if you're operating and you want realistic conditions, we're within 2 to 4%. So I'm nearing the end of my talk here, but there's a couple of slides that I think are cool examples of how you can use energy interference-free debugging support. So say we have a program and we want to insert elements into a list, and then we want to do an expensive check to make sure that the list is consistent. So like each element's next pointers, previous pointers, points to the element itself. This is a pretty simple list consistency check. Well, if we do that, we might see, so these awfully colored magenta circles correspond to the consistency check happening. If we have one element in the list, then maybe we do some main loop work after we do the check for the one element. That's easy. But then later, we had 2 checks here with 2 elements in the list, and then 3 checks here, and then we kill the device. Now we're not making any progress in the main loop because the assertion is toasting us. So if you want this kind of either beta test or development time assertion checking support to make sure your program logic is correct, you can't use it. The check itself is what's going to kill you. So instead, what we did is we use EDB's ability to manipulate the energy level of the device, continuously power it, then reset the energy level to what it would have been, and then do the main loop work. And so by running it on continuous power, we can make forward progress under realistic conditions, despite the fact that we're doing these invasive checks. So the last thing is we've integrated EDB with other hardware. So Tom mentioned earlier that we're launching a satellite. So the satellite on one side has an application processor that has a magnetometer and gyro. We're going to send this into space. It's going to orbit the Earth at 6,000 miles per hour and collect a bunch of radio measurements. But then on the other side, we have this, essentially. And this is going to be operating as a beta test diagnostics collection platform so that we can monitor the behavior of the system while it's winging around in space under conditions that you can really only get if you integrate this hardware with your application and run under realistic conditions. It's not even like we can emulate this in the lab. I mean, we're going to be in space. There's going to be all sorts of wacky errors. There's going to be all sorts of intermittently available energy as this thing is tumbling and not in view of the sun. So by integrating this together, we have a reliable test framework, and we can do this kind of realistic beta testing and get useful information to help us fix our application if it's not doing quite what we want. So really excited about the space launch. March 23rd is when we're going to send it up. Yeah, we already shipped to the launch company, so assuming everything goes well and there are no surprises along the way, we should be in the sky at the end of March. So cool.
What should we change it?
I don't know. I'll send around a link. I'll send around a link for sure. So yeah, that's pretty much what I want to talk about today. I wanted to give you guys an idea about what intermittent execution is and why it's tough to reason about. I showed you that we have some system support for making unreliable executions reliable despite the intermittence. And I hope that I convinced you that debugging intermittent devices is hard and that this is a good way to do it. And I have these available. If you guys think you'll be using intermittently executing hardware, I can send you some devices too. We have a whole big bag in my lab. So cool. Any other questions?